Hello, 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 everybody. Welcome to the last podcast of Big Idea number 3. I am your host, Mr. Folly, and I hope you are ready to learn a little bit about Beer's Law, learn a little bit about electromagnetic radiation, and all the fun stuff that goes with it. So the first thing we're going to talk about is Beer's Law, and Beer's Law, actually, you're going to be mad at me, is from this lab review Beer's Law sheet, which is on Canvas perhaps, but perhaps not. So Beer's Law, the point of the lab and what we're trying to find is we're going to find either the molarity, the molar absorptivity constant, which will identify a solute like a fingerprint, which is really the slope of a line. When we get to equilibrium, it'll also help you determine the rate law. So like I said, it'll identify a solute. Okay, so the equipment is this dude right here. This is a spectrophotometer and a test tube, which is very often called a cuvette, but it's a test tube as far as we care. Okay, so let's take a look at what happens here. Okay, so it's the Beer-Lambert's law. So what happens is you've got a light source and a monochronometer, which will give you a specific wavelength. Okay, the abbreviation for wavelength is lambda. Okay, so and this wavelength, notice how this is a thick wavelength, is absorbed some by the particles in solution. And then we have a detector over here that will tell us how much is absorbed or not. Okay, so the computer simulation that does this, you can change the width of the test tube, right? You can change the color of the light that you shoot, right? And then you will measure how much the absorbance is. Okay, now imagine if this was darker. I suppose I should use, I hope this is pink. You guys probably make fun of me if it's not, but let's see. Do I have pink? Pink. If this is darker pink, then this would be lighter. See how this is lighter? This is darker green. This is lighter green, but the pink will absorb it. Okay. But that's what happens. So you shoot a beam of light through a test tube of solution and measure how much absorbs or how much goes through, and then you plot that. Okay, so what do you plot again? Okay, so what we're going to plot is, so what we're going to plot is on a graph the absorbance, which we saw comes from that machine, versus the concentration. Okay, so we can set up different concentrations and do dilutions and all that stuff to see what we want to see. All right, so the equation is A equals ABC. The little a is now often shown as an epsilon. Okay, so A is absorbance, and the little a is either molar absorptivity or epsilon is little absorptivity, and that is the slope from right up here. Okay. B is the path length, which is the width of the test tube. I have never seen it be anything but 1 centimeter. C is concentration. My goodness, how annoying. Why couldn't we have just used molarity? And over here, the equations we use, M1V1 is M2V2. That's the dilution equations that we do. Okay, so what mistakes can happen? You can have fingerprints on your cuvette. So remember, this is my cuvette, and if my dirty fingerprints are on here, do you see how that means that this would block more light? So if I block more light, then my absorbance would be falsely too high. If my absorbance is too high, my molarity is falsely too high. Okay, so I didn't talk about picking the peak of a curve, but different colors absorb different amounts. So what happens is, and there's a little graph right here. Let's see if I can pull it up. So looking at this right here, this is the wavelength. So that's wavelength. And this is the absorbance. So what you do is you have the same concentration. So just say we do 0.001 molar. And we check every single or every 50 nanometers. And we find out that this one is the most, this one has the best absorbance. So that's the wavelength I use. So that's it. Not picking the peak of the curve. The molarity will be falsely low. And other substances may be included, could shift molarity in an unknown way. In other words, not going to be picked for your mistake. Not using a blank. So let me tell you what the blank does. So the blank, you know, you got your little flashlight of light right here. Just by being a piece of glass, it absorbs some, right? And just by being water, hey, water, it absorbs some. So what you have to do first is you put in a blank, which just has distilled water, and you'll get a reading of absorbance and say it's like 0.03. Then you have to subtract the 0.03. Okay. The other reason, so if you're doing a chemical reaction where this reaction adds 2 dots a minute, okay, so minute, 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 minute. Okay, so if it's a chemical reaction, we can always use the collision theory and say, not every collision will have enough energy and the right orientation to work out the way that it should. All right, so let's look at the procedure. First thing you do is you put in a cuvette with distilled water into the spectrophotometer, and then you zero the spectrophotometer. Put in a cuvette of different known molarities and record their absorbance. Plot the graph of molarity versus absorbance. This will then give you a slope of a line. The slope of that line is your epsilon. Okay? So, and we find the A in ABC, and that A has now been switched to epsilon. All right. Beer's law is done. The rest of it. Spectroscopy determines the structure or concentration. So we're going to use other spectroscopies for this. The photoelectric effect is light hits the surface of a substance and it kicks off an electron. So here's my substance. Ooh, I'm very not quite what I want to be right now. So I shoot light at it and it could kick off an electron that goes there. Light hits the surface and it can kick off an electron. The energy of the light is the energy of the photon. Energy equals H, which is Planck's constant, times the frequency. So E equals H nu. So we can figure out the energy of a photon by doing this. Light has a variety of energies based upon its wavelength. So notice gamma rays have a very small wavelength, and they are very high energy. If I was shot with gamma rays, I become huge, like the Hulk. I wish I knew how to draw muscular people. I'm going to stop there before I make myself look, well, I'm going to draw myself big arms. And then I become the Hulk because the Hulk is green. That's the gamma rays. And gamma rays are the most powerful, which is why they use them to make the Hulk. Okay. Over here, we have radio waves. No one says, save me from the radio waves. They're so terrible. They're long and they have low energy. We're being bombarded with radio waves right now. Oh no. How do we know this? You could turn on a radio and get a radio station. Note as wavelength increases, frequency decreases. Let me just say this again. Wavelength increases, frequency decreases. That is a most missed question because it's an inverse relationship. As wavelength increases, energy decreases. Right? So remember that. Wavelength and frequency are inverse. Wavelength and energy are inverse. Okay? Typically, we're asked to find the minimum energy to knock off an electron. So you can think of as photons as particles too, which would smack the electrons off. So here's my photon of light, dun, 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 and it hits an electron and doink, shoots it off. Okay? Other equation we have is, on your equation sheet also, frequency equals C over lambda. Nu, this is the Greek letter nu, pronounced nu. The speed of light is a constant, 2.99 meters per second. Lambda is wavelength in meters, but it's very, very, very often given in nanometers, okay? To convert nanometers to meters, we just add e negative ninth, okay? 350 nanometers is 350 e to the negative ninth meters. You use this for math. Use this for math. So you got to make sure you do it in meters because the velocity of the speed of light is in meters per second, so it has to be in meters. Okay. Breaking bonds. Given the energy to break a bond, we use the energy to determine the wavelength or the frequency of the photon used to break it. Watch out for kilojoules. So you might think that something is 300 joules or kilojoules or whatever it is. Just watch out for it. Watch out for moles. And remember, there are 6.02 E23 things, usually bonds, in a moles. 750 nanometers can break one iodine to iodine bond. Calculate the energy to break 2.5 moles of iodine to iodine bonds. I would like to point out there is only one bond between iodine and iodine. Lewis dots, woo! Okay. So that's breaking one. So 2.5 moles of II times dividing bar, and then 1 mole of II is 6.02 E23 bonds, of II. So then 750 nanometers of light. So that means I didn't do this the way that I wanted to. Let me grab my calculator. I know, shame on me for not having my calculator ready. Now it's ready. All right, so 2.5. It's validating my operating system. We'll restart. Okay, so 2.5 times 6.02 E23 is 1.505 E24 bonds. Now here's the thing. If it's 750 nanometers to break one bond, make this smaller. 750 nanometers to break one bond, I need to figure out how much energy that is. So I'm going to scroll back to my equations here. 750 nanometers, that's lambda. So I'm going to start with that. I'm going to change the color of this. Just so you can see I'm doing something else. Frequency equals C over lambda. It said my lambda was 750, so that's 750 E9, right? So remember, you just do E-9. Boop, 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 boop. E-9. Over the speed of light, which is 2.99 E8. And that will give me the frequency. 2.99 E8 divided by 750 E-9 is a big honking number, 3.99 E14. And that is my frequency. But I'm trying to find energy. Dun, 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 dun. Oh, E equals H nu. So if E equals H nu, sneak over to this side, E equals H nu, I'll change colors because that's more fun. Energy equals Planck's constant, 6.626 E-34, times nu, 3.99 E-14. I'm going to put that in there. I just don't have room for it. I guess I'll put it in here, E-14. And my energy would be, second answer times 6.626 E-34. And I get 2.64 E-19 joules. Now I want to show you, I use that 6.626 out of the blue, but it's not really out of the blue. See how that's the value of Planck's constant. See how that's joules, not kilojoules? So that's how many joules I have, 2.64 E-19. Calculate the energy to break 2.5 moles of II bonds. So this is the energy to break one bond, but I have this many bonds. Okay, so E total is 2.64 E-19 times 1.51 E24. So that number times 1.51 E24. Enter, and I get a reasonable number of 399,000. 399,000 joules, which screams to me 399 kilojoules. Either answer is A-OK. Okay, so do you see how this is really, I mean, this is very chemistry heavy, but the rest of it is, I have two equations. I have to use them both to solve for it. So it's a really hard 9th grade honors math question. All right? All right. So spectroscopy types. This is mean, okay? The spectroscopy types. X-rays, the frequency. So notice how my frequency keeps getting smaller and smaller. So these are getting, these are getting longer and longer. E to the 18th, E to the 15th. They're getting smaller. So their wavelengths are getting longer. X-rays have high energy. What do? They remove core electrons. And this is PES. So PES, remember, we've done this before with the little peaks. And let me get a better pen than this one. Okay, so PES is where we have like 1s, right? 1s2, 2s2, 2p6, right? Those are PES. Ultraviolet excites valence electrons. It identifies the molecule or the element, okay? So UV spectroscopy, you need to know that ultraviolet, identity of the molecule or the element, and UV spectroscopy, which is annoying. Visible light, this is Beer's law. Beer's. Energy is medium and excites valence electrons, and it tells you the identity or concentration of a molecule. Infrared tells you it's IR vibrational, tells you the types of bonds and functional groups. Microwaves change the rotation of the atoms and the bonds, the location of hydrogen atoms. I haven't seen that used. You do need to know that they have low energy, though. PES is X-ray, and that tells the electron configuration, which is what I was talking about. And speaking of what I was talking about, I'm talking about being done. What are you talking about? I'm talking about being done. So what am I? I'm done. So to that, I will say toodles.